You're in class with Opio, and in this session we are looking at ionization weak acids, and we shall do some calculations on the pH of solutions of weak acids. A weak acid is the one which does not easily ionize, or which ionize to a very small extent when in aqueous solution. And the definition we are going to be using here is going to be the one of Arrhenius or the one of the Bronsted, but we shall not be applying the definition according to Lewis in the pH calculations anymore. So a typical weak acid include acids like most organic acids, for example ethanoic acid, formic acid, and some few inorganic acids like hydrofluoric acid, carbonic acid, phosphoric acid, among others. And when we are calculating the pH of these acids, their concentration may not give us sufficient information for us to get the exact value of the pH, because not the whole of it will go into the solution. Therefore, the degree of dissociation must be used in this calculation. If you still don't know what the degree of dissociation is a fraction of the total number of moles of an electrolyte that can go into solution as free ions. For more information, you can check in my previous videos. We covered that already. And if we consider now a weak acid, we can call it a HA, and we label it with initial concentration. Consider weak acid HA of a known concentration C, and maybe the degree of dissociation is alpha, which will dissociate partially in solution to produce hydrogen ions and the anion. Now, if the initial concentration of the acid is C, that is before dissociation, there will be no hydrogen ions and there will be no anions produced in that solution. And then if alpha of C can react, because alpha percent of C can react, it means alpha of C will react to produce alpha of C, hydrogen ion, to produce C alpha, the anion. So this makes, at equilibrium, we shall remain with C, original amount of the acid, minus alpha C, and if you simplify that, it becomes C into 1 minus alpha. Then the one of hydrogen ions formed at equilibrium will be C alpha, as well as the one of the anion, also C alpha, because they are produced in the ratio of 1 to 1. Then if we apply a law of mass action to this equilibrium, we shall obtain an equilibrium constant Ka, given by the product of molar concentration of hydrogen ions and the molar concentration of the anion divided by the molar concentration of the acid. Now, the Ka is known as the acid dissociation constant, and we are going to use it in most of our calculations. Now, our assumption that we are going to take here are actually two. The first one is that the molar concentration of hydrogen ions and of the anion are the same. That can be seen from the equation. They are all being produced in the ratio of 1 to 1. And the second assumption is that since the acid is weak, its degree of dissociation is so small such that the concentration of the acid almost remains constant after the ionization or at equilibrium. Therefore, the molar concentration of the acid at equilibrium is going to be approximately the original mole, which is actually C. Now, if we substitute that in our expression, it becomes an equation stating the acid dissociation constant Ka is equal to the molar concentration of hydrogen ion squared divided by the original concentration of the acid. So we are interested in calculating the pH of the solution of the weak acid, and the pH is negative logarithm to base 10 molar concentration of hydrogen ion. So in this case, we need to make the molar concentration of hydrogen ions the subject. Doing that, we come up with molar concentration of hydrogen ions being the square root of Ka times the original concentration of the acid. Hence our pH can be negative logarithm of the square root of Ka times C. Now let's look at the degree of dissociation of weak acids. From our equilibrium equation, we already have the molar concentration of hydrogen ions at equilibrium, as well as the one of the anion at equilibrium, and we also have the one of the acid. So if we substitute that, if we substitute those values into the Ka expression, the very first one, we shall come up with Ka being alpha C, that is molar concentration of hydrogen ion, times alpha C, which is the molar concentration of the anion, divided by C into 1 minus alpha, which is the molar concentration of the acid at equilibrium. Now, we can simplify this further. You can see the C reducing, so that we come up with C alpha squared over 1 minus alpha being equivalent to Ka. Now, since the acid is weak, the value of alpha is far smaller than 1, such that when we have 1 minus alpha, it almost remains as 1. So we're going to approximate that. Since it is like that, our Ka can finally be expressed as C alpha squared. And this equation, you can use it to calculate the value of Ka if you are given the degree of dissociation of the acid and the initial concentration of the acid. You can also use the same equation to calculate the degree of dissociation of the acid if given the value of Ka and the initial concentration. As well, you can use it to obtain the concentration of the acid if you have the value of Ka and the degree of dissociation. Well, the degree of dissociation of this acid therefore can be given as the root of the Ka divided by the initial concentration of that very acid. So let's look at the first numerical problem that we have at hand. We have the pH. Calculate the pH of a 0.01 molar solution of acetic acid, given that the acid dissociation constant Ka is 1.8 exponent negative 8 moles per decimeter cubed solution. We have to start by writing our ionization equation. Now, this is the first number. We're going to follow the first principle. The rest we may go faster. So when we pull out the equation, we see the acetic acid producing the acetate ion and the hydrogen ions. Now we're going to use this information the way we see them. So from there we just obtain the Ka expression, the molar concentration of hydrogen ions times the molar concentration of acetate ion divided by the molar concentration of acetic acid, giving us the Ka. So assumption 1, the molar concentration of hydrogen ions is equal to the molar concentration of the acetate ion, because they are produced in the ratio of 1 to 1. And the assumption 2, the molar concentration of the acetic acid remains almost constant, equivalent to the original amount, which could be C, and that is 0.01 molar, because the acid is weak and it is only slightly dissociated, which means most of it remains almost unionized. So when we substitute that in the Ka expression, we come up with Ka is given by molar concentration of hydrogen ion squared divided by the initial concentration. Then the molar concentration of hydrogen ions is going to be the root of Ka times C, which when we substitute, we obtain 1.8 exponent negative 5 times 0.01 and the root, giving us the molar concentration of hydrogen ions as 4.243 exponent negative 4 moles per decimeter cubed. Now that we know the molar concentration of hydrogen ions at equilibrium, we can use that to obtain the pH of this solution, which is given by negative logarithm to base 10 of molar concentration of hydrogen ions contained in that very solution. So we substitute there. pH is given by negative logarithm to base 10 of molar concentration of hydrogen ions, and the molar concentration of hydrogen ion there is 4.243 exponent negative 4, giving us a pH of 3.37 or simply 3.4. So that is what the question wanted, and the number has been solved. So let's look at the second task. Our second task, we have been given the pKa of benzoic acid and its molar concentration. Now when you're given pKa, you shouldn't get scared, because we already know if you have pKa, it should have been got from negative logarithm to base 10 of Ka. So if we have that relationship, we can use it to obtain the value of Ka, and when you have the value of Ka, our calculations becomes normal, just like the first example. So let's do this. Benzoic acid is also a weak acid and is partially dissociated to produce the benzoate ion and hydrogen ions. So our Ka expression can be obtained as that. We are using C because the assumption can be taken that the benzoic acid is weak and it's only partially dissociated, therefore its initial concentration is almost the same as the one that remains at equilibrium. So we take the Ka value as our Ka is going to be antilog of negative 4.2. That will be our Ka. So when we obtain the value of Ka, we simply substitute there, or we can substitute the whole of that expression. From here, you have made Ka to be antilog of negative 4.2, and the molar concentration of hydrogen ions from this part would be molar concentration of hydrogen ions equal to 0.01 times Ka under root. So if we carry this, it would be molar concentration of hydrogen ions equal to antilog of negative 4.2 times 0.01 under root, or the square root of antilog of negative 4.2 times 0.01. So we proceed with that, and we find our molar concentration of hydrogen ions as 7.943 exponent negative 4 moles per decimeter cubed. Then after obtaining the molar concentration of hydrogen ions, we have nothing left but to just substitute it in the pH expression, which is negative logarithm to base 10 molar concentration of hydrogen ions. And our pH there is going to be 3.1. If you put in your calculator, the pH value is 3.1. You can check that out. Okay, the third question here, we have been given a degree of dissociation. When they say is 2.3% ionized, which means out of the total moles, only 2.3% can go into solution. And we are being tasked to find the pH of the solution as well as the value of the Ka. Now, we have got Ka being expressed as C alpha squared, and we also have the molar concentration of hydrogen ions being expressed as alpha C. So using this information, you see this question being a very simple question. So what we do here, we just quote. We have not written the equation. I hope you are now used to that. You can write it. The molar concentration of hydrogen ion is going to be alpha times C, and alpha is 2.3 out of 100. So for us to get the molar concentration of hydrogen ions, we shall be saying 2.3 divided by 100 is going to give us 0.023, multiplied by the initial concentration of the acid, which is 0.02. This will give us the molar concentration of hydrogen ions, and if we substitute in the pH expression, will give us a pH of 4.34, and that will be done. Then to get the Ka is given by C alpha squared. The value of alpha is 2.3%, which is 0.023 in terms of fraction. So 0.023 squared multiplied by the initial concentration, which is 0.02, should give us the Ka for ethanoic acid under this condition, and this gives us the Ka of 1.058 exponent negative 6 moles per decimeter cubed. And lastly for today, we look at the last question. We have the pH of a solution of 0.001 molar benzoic acid is 3.59. We are supposed to calculate the acid dissociation constant. Now under this, we need to know that the acid dissociation constant can simply be quoted as Ka, given by the molar concentration of hydrogen ion squared. I'm just simplifying this because from the previous examples we have been doing this from first principle. So if we square that, our molar concentration of hydrogen ions can be obtained from the pH, since we know the value as 3.59. Now that would be the antilog of negative 3.59, and the original concentration of benzoic acid is 0.001. So when we substitute those two values in this expression, we should be in position to obtain the Ka value for benzoic acid. So let's go. Now the molar concentration of hydrogen ion is antilog of negative pH, and we substitute, we get antilog of negative 3.59, which when we substitute in our Ka expression, we come up with the value of Ka as 6.61 exponent negative 5 moles per decimeter cubed. It may look brief, but you can always pause this video and go through the whole calculation, then you check with us. We must arrive to the same answer regardless of the steps you have taken. I've cut some steps out just to make the video shorter and not to make the lesson very long and boring. So in the second section of this question, we are going to find the value of alpha and pH. So the molar concentration of hydrogen ions has been obtained, and we know it is also alpha C. So if the molar concentration of hydrogen ions is equal to antilog of negative 3.59, and also at the same time is equal to alpha of C, it means the two equations are the same. So we simply equate alpha C to antilog of negative 3.95. Or to simplify things, you could simply punch the value of this antilog of negative 3.59. Let's do that. That is going to be shift log negative 3.59. That would give you 2.57 exponent negative 4 moles per decimeter cubed. Then for you to get this value, you are just going to divide it by C. So we have the molar concentration of hydrogen as 2.57 exponent negative 4, and now if you have that value at hand, you're going to say 2.5 exponent negative 7 is equal to alpha of C, and the value of C is 0.001 molar. So you can obtain the value of alpha there. But if you are following up this method, what you simply do is equate alpha C to antilog of negative 3.59, and then you divide by the value of C, which is 0.001. So we substitute there, and we come up with the value of alpha as 0.257, which is equivalent to 25.7%, which means 25.7% of this benzoic acid can dissociate to produce the ions. And then the last part of the question is tasking us to find the pKa. Since we have obtained the Ka, we can only substitute in the expression that pKa is given by negative logarithm to base 10 of Ka, and substituting that value, our pKa is going to be 4.18 for benzoic acid at that condition. So that was the last example we have done in this session, and I hope I've simplified. Where things get complicated, you let me know in the comment section, or you can always contact me. So I've read for you some numbers to try out and find how far you have gone with this concept. You can always forward your answers to my inbox on WhatsApp, or you can direct to my emails, or even leave it on the comment section. You have around 4 questions to do, or oh, there are even more. That's good. So you try out all these numbers and you send for me your answers, of course. Put them in the comment section. I'll be there available to reply to you with the possible answers. Where you feel like you are really so stuck, you can hit my inbox on WhatsApp. I will always be ready to reply to you, and we have a deep conversation as we simplify your chemistry. So thank you so much for your time, and in case of anything, just contact Opio via the WhatsApp number or the email you are seeing on the screen. Please kindly subscribe if you have not subscribed to this channel. Turn on the notification bell so that you don't miss the next session when I upload the video. I hope you are enjoying your time with us. Thank you so much. You have been in class with Opio.